So, in the previous lecture we looked at an elementary flow which is called as a doublet, and you may recall that the doublet was actually constructed by a linear combination of a source and a sink which were of equal strengths and located very close to each other near the origin. So, in that case we showed that the complex potential for a doublet is given as mu by z when we say that the doublet is located at the origin or at z equal to 0. So, what I will do today in this lecture is to extend that idea and show you what we get when we do superposition of a uniform flow and a doublet. And this is a very interesting problem, because as I will show you, this corresponds to flow past a cylinder, a circular cylinder. So, we will try and prove this today using the arguments that we have been working on so far. So, what is the problem saying? Let me show you in terms of schematic. What we are saying is that if we have a doublet which is located at the origin, okay, so this is the origin and we have a doublet. So, we have some flow patterns here, right. This is what we derived in the last lecture. So, we have some flow pattern near the origin which is because of doublet, and I superpose or I include a uniform flow over this doublet. So, this is uniform flow, all right. So, when you add these two, we are going to answer what is the resulting flow pattern. That is one, and we will show that this happens to be the special case of flow past a cylinder. So, let us get started. Okay. Let us see how this works out, and we will again do it by first principles, which is to go with the complex potentials which have been constructed using complex variables. So, we can write that for this problem of the uniform flow, let us say of velocity u and oriented along the x direction, that is very important here. So, what happens to when you add uniform flow with a doublet? Doublet may be of strength say mu. Okay. So, what do we get? So, we can write that the when we put these two together, the new complex potential should be u times z plus mu by z, where the doublet is centered at the origin. So, this is the doublet, right, the complex potential corresponding to a doublet, and this is the complex potential corresponding to a uniform flow which is oriented along the x axis. So, I want to now derive what do we get when we add these two potentials. So, as usual, let us again start with the polar form of our coordinate. So, we can write this as u r e I theta plus mu by r e I theta, right. So, we can write this as mu r e I theta plus mu by r e minus I theta, and then we use the definition of the exponential of a complex number which is e I theta here. So, we can write this as, in terms of cosine and sine functions, I can write this as u r cosine theta plus iota sine theta plus mu by r cosine theta minus iota sine theta, and we can combine the real terms, in one expression in the imaginary terms. So, we can separate them out. So, we can write this as, say, u in this case r plus mu by r cosine theta plus iota sin theta of u r minus mu by r. Okay. So, I hope that so far this is very routine stuff for you now. So, I can say this is going to be the sum of the velocity potential plus the plus iota times the stream function. So, clearly the velocity potential is u r plus mu by r cosine theta, and the stream function is u r minus mu by r sin theta. Okay. Now, note that I did not say anything about what is the magnitude of velocity or how does the velocity compare against the doublet strength, right. Now, what I am going to present to you now is sort of a, you can consider this as one of those thought experiments, that what if I could say, right, what if I could say that at some distance, say r equal to a, okay, at some radial distance a away from the origin, the number a is such that I could write, for instance, at r equal to a, psi which becomes u a minus mu by a sin theta. What if at some distance a this becomes 0? Okay. What if at some distance a this becomes 0 for all values of theta? So, clearly sin theta will not be 0, but rather we will say that u a minus mu by a is 0, which implies that this distance a square, or rather square of the distance, is mu by u, or I could say mu is a square u. So, we have some distance, a real number, which when squared and multiplied by the strength of the velocity field gives us the doublet strength. Now, that is a fairly easy thing to see. We need not even talk about assuming some distance a, but what we are saying is that at some distance a this must be satisfied. A could be either small or large depending on what is the strength of the doublet and what is the velocity field that we are trying to impose, but this must happen somewhere because a can go from 0 to infinity. So, this equation must be satisfied at some location r which is equal to a. Now, if this is a case which happens, let me say for all theta, then at this distance clearly psi would be 0. So, psi would be 0 at r equal to a. Since psi is 0 at this distance, it is clearly a streamline, right, because the stream function value is a constant on this circular line. So, recall what r equal to a means. If we draw the complex plane, in this case this is the origin, right. So, r equal to a would mean that we are at some distance r equal to a, and the circle passing through that distance, that is a circle. On this circle here, all points on this are in equal distance from the origin, psi is 0, okay, for all theta. So, recall now that we had a doublet at the origin. So, what we had was a doublet flow which was right here. So, we had a doublet here at the origin, and we had a uniform flow outside. Since psi equal to 0 is a streamline, think about what I am going to say now, that can you make out that this surface is a line which separates the doublet from the uniform flow entirely. What I mean by that is that uniform flow that starts from outside this cylinder remains confined outside the streamline, at the streamline which starts outside this surface psi equal to 0 remains confined outside, and the doublet remains confined to this region only within the cylinder. So, I am trying to draw a green line here which is very close to the cylinder surface, just to make sure that the two lines do not coincide, but basically it is the same r equal to a line. So, the effect of the doublet is confined to this region only, right. So, the effect of the doublet is confined, if I could probably try that, it is confined to this region only. Okay. And outside this streamline, which is now what I am calling as a dividing streamline, the uniform flow prevails, or the effects of the uniform flow prevail. So, note that now we can say that the psi equal to 0 streamline, which is at a distance r equal to a, confines the doublet entirely, within this circle, and the uniform flow is deflected in such a way that it is entirely outside r equal to a. The point that I am making here is that the dividing streamline has ensured effect of the doublet remains within the cylinder, and the uniform flow sees the dividing streamline as an obstacle, so to say, and so the uniform flow gets deflected around this, just because r equal to a line happens to be one across which mass transfer cannot happen, or there cannot be no fluid flow, just because of the way the problem has been set up. So, now let us begin a simple thought experiment. So far we have only looked at two things. We have superposed a doublet with a uniform flow. Now let me talk about a thought experiment with you, okay, and this would require you to just go along with or think about what I am saying, and we will do it very slowly. So, now we see that what happens when you have a doublet with a, say in this case, the uniform flow, right. Now, I know that r equal to a is a streamline, and across this there is no normal component of velocity. In this case now, if I was to slide in a cylinder, a hollow cylinder which is of radius a, if I was to gently slide it in into this plane such that it is centered at the origin and it coincides exactly with this streamline which is at r equal to a. So, say let me do this first. So, think about this in this thought experiment. I slide in a cylinder which is hollow and which has a radius a, and it sits exactly where the streamline psi equal to 0 is located. Now, at this point when you slide it in, there would be no change to the flow, because the surface of the cylinder would actually become a streamline, because there is no normal component of velocity. Now, note that at this point, since the flow remains the same, the flow would still remain the same, it will be frozen. Now, what I am going to do is, in my thought experiment, I will pull out the doublet. So, I pull out the doublet from within the cylinder some way, this is a thought experiment. So, I can just go in, pull the doublet out. What would happen to the flow now? I am sure you can imagine, even when I pull out the doublet, the flow will not change, because the uniform flow would be deflected because of the shape of the dividing streamline, which is the surface of the hollow cylinder. Now, finally, after I have pulled out the doublet, I pour in the same, let us say, concrete. Maybe the cylinder is made of concrete or some steel, let us say. I pour in molten steel and I allow it to solidify within the hollow cylinder or the hollow cavity, and it becomes a solid cylinder, a solid object. Would the flow change? No, again not, right. So, the flow will again not change, and so what we would have achieved as part of this exercise of this thought experiment, that we gradually put first a hollow cylinder, a shell, then we pull out the doublet, and then we pour something, the metal or the concrete into this hollow cavity to fill it up completely. There would be no change to the flow pattern, and we would still get the same flow that you are seeing on the screen. What have we achieved here? By doing this, or by combining the doublet, so by combining the doublet with uniform flow, we have achieved flow past a circular cylinder. Let me say this for now, which I would even elaborate a little more in the next lecture. This is without circulation. Okay. So, the flow pattern that we would have achieved now would be this. So, we will have a cylinder sitting here at some distance r equal to a, and this is a solid cylinder. So, let me indicate it so. And you would have flow going around it, so to say. Okay. Let me also define my coordinate axis here, just to make another argument very soon. Now, this is a very special solution, because what it predicts is that on this cylinder, since the flow goes over it and we have two coordinate axes x and y, this solution predicts that force along x is 0 and force along y is also 0. And this happens because the flow is symmetric about both x and y axis. So, it is the same flow, right. If you were looking from the x equal to 0 axis, which would be the vertical line, if you see either side, you will see the same flow pattern, and if you see from y equal to 0 line, it would again be the same flow pattern, in the sense that it would be a mirror image. So, because of the flow being symmetric, there is no force which is exerted on the cylinder, and more importantly, it is also the case because viscosity has been neglected. We are not discussing any shear force in this case. But in reality, what you know is that a thin boundary layer develops, right. So, a thin boundary layer develops around the cylinder, which also separates at some point, and we get a wake that is formed. All right. So, when the wake is formed, we get considerable drag force. Okay. So, this would be the real flow around the cylinder. So, when we have a real fluid which was basically which is not inviscid, so you will get viscous drag and also pressure drag or form drag as it is called, because the flow separates. So, there would be some point where the, let us say at this point the flow separates. On either side, on one on the upper half, the other one on the lower half maybe. Okay. So, there definitely Fx and Fy will not be 0. However, what we have derived, even though it may seem that it does not match the real flow, what we have derived is actually a very unique case, because the solution is still valid in some regions of the real flow as I have shown you. So, even if the real flow is, let us say, uniform flow coming over a circular cylinder, right, but there would be some differences as I have shown you here. So, there would be some differences, but even then the flow that we have derived is still applicable outside the boundary layer. So, it is applicable outside the boundary layer and upstream of the separation point. That is very important. So, until the flow does not separate, our solution is still valid. So, what I mean by that is that our solution is still valid, so to say, in this region. All right. So, here we can still apply this flow, but as soon as we get close to the boundary layer or in the boundary layer, this solution will no longer be applicable. So, conventionally the way the earlier CFD solvers used to work was that they used to calculate flow outside the boundary layer using the same approach, that they would solve using a potential flow solution, which is what we are doing. We are solving for potential flows, right, irrotational flows. So, they would solve outside the potential flow using this approach, and then they would sort of stitch the solution or marry it to the solution which is computed from within the boundary layer, right. So, and the pressure field basically used to come from outside. So, the pressure comes from outside, it is brought in at the edge of the boundary layer, so to say, right. So, you get pressure here in the direction normal to the surface, let us say you get the pressure there and then you bring it within the boundary layer, you impose it within the boundary layer. So, that is how the earlier CFD solvers used to work. Now, with fairly good advances in computational, a number of calculations we can do, and also because of better computers that we have nowadays, we can do this without even solving for the irrotational flow outside. We can solve the full scale Navier-Stokes outside the boundary layer. But this is what is a key feature of this flow. I mentioned that this is without circulation. As we will see in the next lecture, if you have flow with circulation, then there can be a force that can be exerted on the cylinder, and that would be specifically in the y direction, that we will call as a lift force, but that we will discuss in the next lecture. So, just to summarize now and to also give you some sense of how the to complete the entire discussion on this problem, what we have come up with so far is a complex potential which is given as u z plus u a square by z. Recall that mu is u a square. So, we can write this as u z plus a square by z. That is a complex potential for flow past a circular cylinder without circulation. Let us try and calculate the velocity field for this flow now. Now that I have shown you from the stream function approach, we can also calculate the velocity. So, we can take df dz, which would be w. So, that would be u 1 minus a square by z square. Now, using the fact that z is again in polar coordinates given as r square e to the power 2 I theta. So, z would be r e to the power I theta. So, z would be r into e to the power I theta, z square becomes r square e to the power 2 I theta. So, we can write this as u 1 minus a square by r square e to the power minus 2 I theta, and because I want to compare this with, remember, u r minus I u theta into e to the power minus I theta, well, I could sort of use this and write this as u e to the power minus I theta times e to the power I theta minus a square by r square e to the power minus I theta, which is basically just pull out and e to the power minus I theta out. So, you get e to the power I theta in place of unity or in place of 1 here. So, now it is easy to compare and separate out some terms. So, this cancels. So, clearly u r would be, now remember, e I theta minus a square by r square e to the power minus I theta will actually give me cosine theta plus iota sine theta, and this will give me cosine theta minus iota sine theta. So, we will have to combine the real and imaginary part. We need to separate them, combine the real terms, separate them out, combine the imaginary terms, separate them out, and what we will get is u r to be u cosine theta 1 minus a square by r square, and u theta will be minus u sin theta 1 plus a square by r square. So, though I have jumped a few steps here, I fully expect you to be able to work this out. So, if you look at this expression, note that u r is 0 for r equal to a. So, which is precisely the psi equal to 0 streamline. So, u r remains 0. So, there is no radial component of velocity across that streamline, which is good that we verified our earlier finding. But let us also look at u theta. So, if I look at how u theta changes, so let me say if theta is between 0 and pi, clearly u theta would be, what do you think, positive or negative? Note that 1 plus a square by r square is always a positive number, because r square would always be a positive number, a square is anyway positive. So, clearly the sign of u theta will depend on sin theta. So, when sin theta is positive, which is what it is between 0 and pi, u theta would be negative, and when theta is between pi and 2 pi, where sin theta is negative, u theta would be positive. So, in this picture that we have, right, which we will maybe can draw again now that we have a lot of other things going on in that figure. Okay, so what we are saying is, from the point of view of the origin, theta basically goes in this direction, right. So, between 0 and pi, u theta is negative, which means that the flow must be in the clockwise direction. So, that is what I have shown here. When I draw the velocity vectors going from left to right, they are actually in the clockwise direction. and when you go from pi to 2 pi, so pi to 2 pi would basically mean you are in the lower half of the cylinder, then you get flow in the counterclockwise direction, right, with the positive sense of theta, and that is what we also see. Okay. More importantly, on this surface r equal to a, as I said, u r is 0 for all theta, but we also see that u theta can be 0 at two locations. So, when is u theta also equal to 0? This will be when sin theta is 0, which implies theta is either 0 or pi, right. When theta is 0 or pi, sin theta will also be 0, which means in terms of coordinates, say r comma theta, I can say the velocity u vector, if you want to put it, this would be 0 for which values of r and theta. So, this would be 0 when r is a, theta is 0, or when r is a and theta is pi. At these two locations, the velocity is 0. And where are those 2 points? So, those 2 points are these 2 points, right. This point is a comma 0, because theta is 0 there, and this point is a comma pi. So, at these 2 points u is 0, and these are called as stagnation points. These are stagnation points of this flow. So, stagnation points are those where the static pressure is maximum. In this case, the static pressure would be the same at both of these 2 points, and that is the reason again why the cylinder does not feel any force along the horizontal direction. All right. So, this is all about flow past a circular cylinder obtained by combination of a uniform flow with a doublet. And we saw in this case that the total force on the cylinder is 0. So, there is no force along the horizontal or vertical direction. What we will do in the next lecture is to derive a solution in which there is some force over the cylinder, but that would only be because of pressure. As we are dealing with irrotational flows, there is no shear force on any solid object. So, there would be only form drag, or if you want to put it this way, right, and we will derive what the solution would be using the same complex potential method. Okay. So, I hope that this part is clear, and we will take it further in the next lecture. So, thank you.